Hi, and welcome to section 4.5, Math 232, General Linear Mappings. So again, we're sort of in a bit of a review phase where we're doing a similar thing to what we've been doing for the last little while, but we're doing them in a more general vector space. And it's just maybe a little bit more abstract than what we've been doing before. But really the concept is pretty much the same. And like I've said before, each time you see a general vector space V or a vector space W, you can replace that in thinking about it with Rn, or you could replace it with all n by n matrices over the real numbers. Those are our only two vector fields. Vector spaces. Okay, so here we are. We're going to just look at the more general idea of a linear mapping. So the vocabulary is here. A linear mapping, it means the same thing as a linear transformation, and that is our usual thing where we see that if we take a linear combination of the inputs, we get a linear combination of the outputs. And a linear operator is what the term that we use when we have a linear transformation when the domain and codomain are the same vector space. So if we have a linear transformation from R3 to R3, we could call that a linear operator. The null space, that is the set of all of the inputs to your transformation that map to the zero output. And then the range is the set containing all the possible outputs of a mapping that may or may not be the entire codomain. Okay, so we're just going to take again a look at slightly more complicated mappings here and then determining whether or not they're linear. So let's just make sure that we can read what this is. This is saying we have a mapping, we're calling it a transformation, we're calling it D, and that transformation takes as its input all 2x2 matrices with real entries, and it maps that to a real number, and that real number defined by taking the transformation of each one of the matrices is going to be the determinant of the matrix. And we haven't really talked a lot yet about determinants. This is a bit of foreshadowing here. We're going to have another lecture coming, I think 5.1. So just in a couple of lectures, we're going to talk a lot more about the determinant. But the determinant is a property of a matrix. And we have seen the determinant of a 2x2 matrix. So that we have the determinant of a matrix A, where A is a 2x2 matrix. We sometimes also write it like this, just with the straight bars. So we would have then, this would be the determinant of the matrix with entries A, B, C, and D. That is looking like this, A, B minus B, C. Okay, so we take the product of these two, and then we subtract the product of those two. Okay, this is coming in more detail, but it doesn't matter if you, in the context of this problem here, if you don't recall or don't want to know what is a determinant, it doesn't matter. It's just saying this is what our transformation does. It's going to take a matrix and it's going to turn it into a number under a certain rule. So let's just give an example. Like pretend one of our input matrices was like this, 2, 3, 1, 4. Then what this transformation D is going to do is it's going to go like this. It's going to make the calculation AD minus BC. So it's going to make this calculation 2 times 4 minus 3 times 1. That'd be 8 minus 3, that's 5. So the transformation D turns this matrix here into this number here. Let's just do one more example. If we had some other matrix, 1, 0, let's just put here 1, 5. I don't like that number because it's going to turn out to be the same, minus 3. Okay, then we ask what will D do? D will make that same calculation on this matrix here, and I will take 1 times minus 3 and get minus 3 and then subtract 0. So it'd be minus 3. So it turns this matrix into this number. So each 2x2 matrix is turned into a number via the linear transfer. Well, no, via the transformation D, where we're trying to understand, is D linear or not linear? Now, yeah, let me just stop. I was going to say something, but maybe I won't. Okay, so let's just like have a little visual picture of what's happening. We have over here the domain. The domain is all matrices that are 2x2 with real numbers as entries. And so over here in our domain, we have lots of these guys, all of them. There can be, they're sitting in this over here, and the general one looks like this. Okay, whatever, we have lots of them in here. Okay, we have all of them in there. All the 2 by 2 matrices are sitting in there. And then D happens to them, and D does this operation, which is the determinant of a 2 by 2 matrix, which is AD minus BC, and it turns it over here into a real number. So over here are all the real numbers, and each one of these matrices here maps to some number over here. Okay, so we want to know, is this linear or not? So I mean, you're going to have to show if it's linear, it's closed under scalar multiplication and closed under addition. That would be then a linear closure. Is actually, let me not say closure is not the right way. It's to say what we want to, if it's, well, let me just say, what does it mean for it to be a linear transformation? Let me rephrase that, actually do a better job. Would mean that d of kx is equal to k times d of x. That is the scalar multiplication. And then d of x plus y is equal to d of x plus d of y. That's what it means to be a linear transformation. Okay, so let's take a look at this first property here. Well, we imagine if we take the matrix A, B, C, D, and we operate on that with this transformation D, we will get AD minus BC. Okay, now let's take the input K times A, B, C, D. That input is this K, KA, KB, KC, KD. Okay, and then we're going to operate on that. We're going to operate, apply the transformation to that thing there, just like that. Okay, and then let's just do the calculation. So I would get then KA times KD minus KB times KC. That is equal to K squared AD minus K squared BC. That's equal to K squared times AD minus BC. And that is not equal to K times D of A, B, C, D. So it's not linear. Not linear. All right, let's do another one. These ones are slightly more complicated than the ones we had before, just because we've got two different vector spaces that we're now allowed to talk about. So here's now a transformation, T. This one's called T, and it is taking a vector, two-dimensional vector, and turning it into a matrix. So what our over here, our domain is R2, and what do we have in here? We have R2. We have a bunch of vectors that look like this. The general vector here being x1, x2. Okay, and then we have a transformation, and the transformation goes over here to the codomain, which is all 2x2 matrices with real numbers. That is the codomain. And so here we have all matrices like that. And some, we're not necessarily going to be able to get all of these matrices. In fact, you can see that we can't, just from the way this thing is working. But that doesn't mean that so the codomain is all of them, and some portion of them, let's just say it's these ones, some portion of them will be reached via this transformation. Okay, so this is the a restatement of the transformation. X1, X2, an input. In R2, we apply T, and we get out the vector x1, 1, 1, x2. Now the question is is this linear or not? So then we check, does it satisfy those properties that T of kx will equal kt of x, and will T of x plus y equal T of x plus T of y. That's what we need to check to decide if a transformation is linear. Okay, so let me just then say, okay, that is the case if the input vector is x1. This here is the case if the input vector is x1, x2. If the input vector is y1, y2, we apply the transformation. Then we would get y1, 1, 1, y2. All right, so let us now add together the two inputs, x1, y1, x1, x2 plus y1, y2. That gives me this, x1 plus y1, x2 plus y2. Okay, I've added together the two inputs. Now I'm going to apply the transformation to the sum of the two inputs. I'm going to apply the transformation to this vector. This is x plus y. And let me apply it via the rule. What happens is I get the rule here stated up here is to take the first input and stick it here, put a 1 here, put a 1 here, and take the second input and put it here. That's what we did when we formed these two as well. Okay, now let me add those two together, because right here, this guy right here is T of x. I'm calling this guy x and this guy y. And this guy here is T of y. This guy here is x plus y. And this guy right here is T of x plus y. Okay, so let us now add together T of x plus T of y. That is going to be T of x. We already have that figured out. T of y. Okay, we'll perform the addition. Okay, these are not the same. I'm going to circle where it's not the same. This guy here, T of x plus y, is not the same as this guy here, which is T of x plus T of y. This is not linear. It's just a little bit more complicated to check for linearity when you're going from one vector space to another vector space, where it's not going for, say, from R2 to R2 or R3 to R2. It's actually really quite easy to see in those cases. It's a little bit more difficult in this case, but the concept is exactly the same. You're just checking these two properties. Okay. We have the same concept of range and null space. So if we have a linear map, now we're talking about linear mappings. If we have a linear mapping, then the range is all of the outputs for which there is an input in the so I imagine taking all of the inputs in the domain, and I ask, what are all the possible outputs? That's the range. Like it always was, it has always been that way. And so again, we could be thinking of this as R2 to R2 or something like that. Okay, the null space is exactly the same. It's all of the vectors. It's all of the vectors in the domain which result in the zero vector of the codomain. Okay, so here we have a mapping, and we're going to ask this question first, and we're going to do some null space and range calculations as well. But let's ask this question here first. We have a mapping. L, which is defined right here, R3 to R3. So this is a codomain of R3 and a domain of R3. The input domain is R3, the output codomain is in R3. Okay. we have the linear mapping defined this way. We're wanting to know, is this a possible output? Is this in the range? Is there any input vector to which I can apply this transformation and end up with this output? That's what the question is asking. Okay, so let me write that down. Can I write 203, the output, equal to x1 plus x3, 0, x2 plus x3 for some input vector? Okay, well, you can see what has to happen for this to be possible. I have to have a system where x1 plus x3 would be equal to 2, and where x2 plus x3 is equal to 3. And that is 3 unknowns, two equations. So I'm going to set up a little linear system here. I don't have to do anything to read off the solution here. We've got 2 leading variables, and we've got no leading variable here. x3 is free, x2 is 3 minus t, and x1 is 2 minus t. So an input vector, x, is to give this output vector looks like this. It is the solution to this linear system, and that was looking like this. We've got x1, 2, 3, 0, and then we've got t times minus 1, minus 1, and 1. I'm claiming that for this linear transformation, all of these vectors, there's an infinite supply of them that will give you this output. So let's just check. We'll just let t equal to 1, and then I have then that would give me an x equal to 1, 2, 1, and then let me apply the linear transformation to 1, 2, 1. What does my linear transformation do? It adds x1 and x3. That's 2. It doesn't do anything to the middle, just makes 0. That's this right here. And then the third component is computed x2 plus x3. x2 plus x3, that's 3. So this input vector right here gives me this output vector. You can choose any other value of t, and that will happen as well. Okay, so the answer to this question is yes, y is in the range of L. It is possible to find an input such that you can get that y value as an output. Okay, here's another question. Find the basis for the null space. Okay, this is a mapping where what's happening is we're taking, again, our domain is all these 2 by 2 matrices, whichever ones we like. They all have this form A, B, C, D, where A, B, C, and D are real numbers. And then our transformation is going to maneuver us over here to a codomain, which is consisting of numbers 2, 3.6, root 2. All real numbers are in here. That's the codomain. And the rule that's being applied coming across here is A plus D. So we're taking our input matrix, we're simply taking the sum of the diagonal elements on the 2 by 2 matrix. We're asking, what is the null space? So we want to know which vectors, which inputs, A, B, which these are all the inputs look like this, will give an output of 0. And that's because that's what the null space is. Okay, so in order for this thing to give an output of 0, when what the rule that you're doing is your output is going to be the sum of those two things, then that means A plus D is going to have to be equal to 0. It isn't going to matter what B and C are, because they're not even included in the calculation. So they're kind of irrelevant. They are irrelevant. They can be anything and doesn't affect whether the output is going to be 0 or not. Okay, so it's A plus D, or D is equal to minus A. So it is all matrices of the form A, B, C minus A. You can see that all matrices that look like this. When I add these two things, I'm going to get 0. So what does the basis look like? Then the basis is this. The basis for the null space is well, certainly this guy here, right? That's when both of the diagonal elements are 0, and then the off diagonal element, this guy, is a 1. It isn't going to matter. I'm going to get 0. And then here's a linearly independent vector with the same property. There's 2 linear, and then what's our other possibility? So all linear combinations of these vectors in our vector space consisting of all 2x2 matrices will result in a 0 output. So the basis for the null space is this thing, and it is of dimension 3. Okay, we have a generalization then of the Rank-Nullity theorem, and in here, so we've previously said the rank of a matrix. We recall this. Recall, if we have a matrix A, let's just take a matrix as an example, 1 0 0 0 1 0 0 0 0. Okay, the rank of the matrix is the number of leading ones. This is a rank 2 matrix, and that is we can more generally instead of representing our linear transformation in a matrix and then row reducing and calculating the number of leading ones and getting the rank, we could be thinking this here of the rank of L. What is the rank of a linear mapping? It is the dimension of the range. So the rank of a linear mapping is the dimension of the range. You will recall when we've been talking about matrices that the range, that the outputs are linear combinations of the column vectors. If I was to take this and I would multiply by x1, x2, x3, I get x1 times 1 0 0 plus x2 times 0 1 0. I don't get anything from this column. It's all zeros. So I see here that that I have 2 independent vectors, and all the vectors that look like this are the range. The range is of dimension 2. It's a rank 2 matrix. So the rank of a linear mapping is the dimension of the range. So I'll just write that like this. Rank of L is the dimension of the range of L. Okay. So the rank null, and we've just seen an example, the nullity of L, that's the dimension of the null space. Let's just remind ourselves of that. Nullity of L is equal to the dimension of the null space of L. Okay, and then we're looking here that the dimension of the input vector space, if you will, of the dimension of the domain of the transformation is n. And when it's been sort of, if we have had the situation of a mapping from say R4 to R2, then this has been the value of n, right? That is what n is. And we've seen that as the like in this case here, n is 3, right? It's this size right here. Okay. All right. So let's do an example. I'm going to try to find the basis for the range and a basis for the null space from this linear mapping here, and we're going to verify the Rank-Nullity theorem. Okay, so the first thing we're going to do is we will we'll be thinking like this. L is going to be the matrix representing this linear transformation is going to be of size m by n. And in this case, m is going to be 2 and n will be 3. Let's see that. Okay, we don't mix up which one is m and which one is n. So we can figure out what L is by applying the transformation to the standard basis vectors in R3, because our inputs are in R3. Like that. And I get here an output of 1, 1. Here I get an output of also of 1, 1. And here I get an output of 0, 1. So the matrix representing this linear transformation is this guy here. 1, 1. That's this guy as a column. 1, 1. This guy as a column. And 0, 1. This guy as a column. I could do a quick check. I know that my inputs are three-dimensional. Therefore, I would be expecting to multiply this by x1, x2, x3. If that dimension didn't work out properly, then you know that you've got a mistake. Okay, so you can sometimes check by just knowing the size of the input and the size of the output. Make sure that you've got the dimensions of your matrix correct. And so you can see here n is 3. We've got 3 columns and 2 rows. And I'm just going to put the power into my first. Just attach the power to my laptop there. Okay, so we've got this thing here. Now what we want to know is we want to talk about the null space. So in order to find the null space, we want to know which input vectors give an output vector of 0. We're solving this here. L x equals 0. This is a linear system. Our usual row reduction thing happens here, and we get 1, 1, 0, 0, and 0, 0, 1, 0. And we have the leading variables. And so we have here, there's no leading variable here. So we have that x2 is a free variable. I'm going to just call that t. And then we have that x3, this last row here, that tells me x3 is 0. And then this first row here is telling me that x1 is minus t. So that means the vectors that will, the input vectors in the domain, which will give the 0 vector in the codomain, look like this. T times minus 1, 1, 0. So then the basis for the null space is minus 1, 1, 0. And the dimension of that is 1. So the nullity of, right, like this, the nullity of L is 1. So we already know, in fact, we know that n is 3. So we now actually know already that the range, the dimension of the range is 2. By the Rank-Nullity theorem, we know that. But we're going to be verifying the Rank-Nullity theorem here. So we're going to go ahead and figure out what is the range of L. Well, we've already row reduced the matrix, and it is, we can see that these are the 2 linearly independent columns. So looking here, we know that the range of L is the all linear combinations of those 2 columns. So the range of L is the span of those 2 columns. Those 2 columns. And that means, and then if I guess I could say a basis for the range of L is, and I would just write that without the word span there. Those are the 2 basis vectors for the range of L. And you can see here, there's 2 of them. So the dimension of the range of L is 2. And indeed, we've got the nullity is 1. The dimension of the range is 2, the rank is 2, and n is 3, and 1 plus 2 is 3. So we are verified Okay, let me just show you something else just about this. We have this matrix here, 1, 1, 1. This is L, 1, 1, 0. Now let's just multiply this by all possible inputs. This is just another way of seeing what's going on with the range. So we're going to multiply this by all possible. This is all possible inputs. And one way of looking at this matrix vector multiplication is that the multiplication is a linear combination of the columns. Okay, and then I could rewrite this, seeing how this is the same in both cases. I could write this like this. So the possible outputs that you can get is some number times this vector plus some number times that vector. That's exactly the basis for the range, those two vectors. Okay, we can compose linear mappings. And that means that we can do one input and then do a second input. I'm thinking of it like this. We have some sort of input, and then we have linear mapping number 1. Let's call that L, and then we come down and we get some output from that, and then we have linear mapping. Then we have linear mapping number 2, and then we get a final output. And if we are thinking of putting these together in a big box, then what we're thinking is that the relationship between the input and output here is first L and then M, and then that is a composition. And that composition, the order that I've drawn it is this one here. First we perform L, and then we perform M. So first we perform L, then we perform N. So the order is important. Watch the order, okay? Because we have observed and we've spent a bunch of time, and a key feature is that matrix multiplication is not commutative. So you cannot just reverse the order and hope for the best. That will land you in hot water. Okay, so let's just take a look at this in R2, and let's look at the geometry of this as well. So I'm just going to concoct an example here. I'm going to have one transformation called L. It's going to go from R2 to R2. It's going to be a shear. Okay, then I'm going to have a second transformation M. It is also going to go from R2 to R2. Clearly, I hope these two things have to match. Okay. The output from one has to be in the right size to go into the next one. Here, that's not going to be a problem. Everything is in R2. On this one, I'm going to make a reflection. I'm going to see what happens when I compose these things. So here's an example of a shear. I'm going to use this example for a shear. So the shear transformation is going to be like this. Okay, that's a shear. And then the reflection is going to be this guy here. This guy is a reflection across the y equals x line. So this is reflect across y equals x. Okay. You can possibly see that. Let's just take this matrix like this, 0, 1, 1, 0, multiply by xy, and I get yx. Okay, there it is. Okay, so now let us compose these things. M composed with L is the matrix M, and then let's apply that to a vector. That is going to be M of L of X, which means we are first going to multiply X by L, and then we are going to multiply it by M. So we're going to go ahead and do that. We know what these are, and I'm going to get this 0, 1, 1, 0, 1, 2, 0, 1, and then I have X. I'm gonna perform this matrix multiplication, and I get this 0, 1, 1, 2, X. Okay, now let me do it the other way around. L composed with M. And in that case, I am going to take my vectors x. I am first going to multiply them by the matrix representing the transformation M, and then the other. So it's still in the opposite order. Okay, let me go ahead and do that. I'm going to get multiplying those two matrices together. Okay, and you can see they're not the same. Those two matrices do not commute. There's that guy and that guy. They are not the same. So it matters in which order that you do the operations. And these are both easy to see geometric operations. So let's have a picture of what's going on. We'll first do the L composed with M. So L composed with M, I'm going to ask you to imagine a square here like this, of which this point here is 1, 1. I'm just going to shade this so we can see the difference. Now the first, in this case, L composed with M is a reflection. So I'm doing M here, which is a reflection across the y equals x line, which is this line here. So I imagine taking all vectors in this box and reflecting them across the line. I'll end up with this here. Okay, the ones that are down here end up here. They're reflected across the line. This is still the point 1, 1. And then I perform L, which is a shear. And I get this guy here. I just now performing L, this right here, the shear. Okay, and that takes this square box with the ones shaded, so I can see where those inputs have come from, and it makes a shear here like this. Totally happy with that drawing. Let me try it again. Trouble with parallel line there. Like that. And this point right here is now 3, 1. Okay, so that is L composed with M. Now I'm going to do M composed with L. Let's start with the same box of vectors, and look like that, 1, 1. And I'm first going to shear. That is going to look like this. Here is the line y equals x, and this shear will look like this. And we've got the guys here in the bottom half. Okay, so that is the shear. This point is 1, 3. Now I'm going to do the reflection. I'm going to get this guy here. I've got the line y equals x here, and it is going to look like this. Like that, with this point here being 1, 3. This is not right. Here, let's fix that. Okay, there we go. It's not the same. That's the big revelation. It's not the same. So you can see this picture here does not look like this picture here. That's because it matters which order that you do these geometric operations in. And you can see that it matters, in fact, even without drawing the drawing, because you can multiply the matrix of the two transformations together in both of the two orders and see that the net effect is on each vector is going to be different. Okay, so you can compose transformations, and the order in which you compose them definitely matters. Okay, the next point about mappings is, can we go back? Can we go backwards? And the answer is sometimes, not always. And that's actually an important distinction. So let me just make some comments about this. if M is the inverse of L, then L is the inverse of M. Okay. Key point, not all mappings are invertible. We've seen earlier that not all matrices are invertible. And since we have all matrices represent linear transformations, it immediately follows from that that not all linear transformations have an inverse. If the inverse exists, it is unique. Okay, there's not more than one of them. If a mapping is invertible, then the null space of the mapping is precisely the zero vector in the domain. And the range of the mapping is precisely the codomain. Let's think about this one. This one's easy to see, actually. Imagine the situation where you have some domain. Which way we're doing linear mapping? We're going from W. Uh-oh. No, we're not. Let's just look at the wrong one. That's the inverse. We're here. We're going from V. And we are moving over here to W. We're mapping from V to W. That's L. Okay, M is the one that's coming back. Okay. M, okay, here, I just want to make this point. If we can come back, and that's a big if, this will be M, this was previously known as M, but the M is then denoted to be the inverse, if we can come back with this notation. Now, let us imagine this case. What if the null space, we have a zero vector over here, and it's coming to the zero vector over here? What if there was another vector over here that's not zero, let's just call it V1, that mapped over here also to zero? What if that happened? Then I'm over here in this W land over here, and I'm like, hey, I'm at zero. How would I know? How would I know if I came from here or if I came from here? I would have no way of knowing. All I would know is that I'm over here at zero. And so then I would not be able to go back. So this would not have an inverse. So you can sort of see why if it's an invertible mapping, there is only one vector in the input that maps to the zero vector over here, and it is the zero vector. Okay, so here's a question: Are these two inverses of one another? We have two mappings, and we're wondering if I go like this, L of x1, x2, and I get some output, y1, y2, and then if I take M of y1, y2, do I get x1, x2 back? That's what we're asking. Because if that happens, then they are inverses. If that doesn't happen, then they're not inverses. So one way of doing that is to form the matrix for the linear transformation of L. There it is, 2, 3, 1, 3. How did I get that so quickly? Well, that's L of 1, 0 is 2, 1, and L of 0, 1 is 3, 3. Okay, and then I formed the matrix for the transformation M, and that is going to be 1, -1, -1, 2, like that. And similarly, I could have got that by looking at what happens to the standard basis vectors under that transformation and putting those into the matrix as columns. Looking at that. Okay, I've got two matrices. Now, if they are inverses of one another, then this will happen. Because you expect to be back where you started from. And that is what you multiply by if you're going to get back where you started from. Okay, so what things are an inverse of one another if when you multiply them together, you get the identity element. This is the identity element for a 2 by 2 matrix. This one, number 1, is the multiplicative identity element for multiplication of numbers. So if I want to get to 1, I have the number 2, then I multiply by 1/2 and I get 1. So these two things are inverses. They're multiplicative inverses. So I now can just try it out. 2, 3, 1, 3 multiplied by 1 minus 1 minus 1, 2. And I got here -1, 4, -2, 5. Clearly not this guy. So these guys are not inverses. And we can see this, in fact, even with just an example. Allow me to take the transformation of 1, 1 under M, and I get 1 minus 1 and -1 plus 2, and that works out to be 0, 1. Now let me take the transformation of 0, 1, and I get under L, and I get 3, 3. So I didn't get back to 1, 1. Okay, so I'm in this situation here. I've got my little boxes, and into this box, I put the vector 1, 1, and then I got out the vector, 0, 1, and then I went into the next box, L, and I got out the vector 3, 3. Okay, and then I see that these are not the same. So these are not inverses. Okay. This is a hard example, I think, in some ways, and it's just requiring us to think carefully about what we're being told. And there's many different answers to this question, but we want to provide a linear mapping. We want to provide a linear mapping such that we start with all 2 by 2 matrices. We end up with a 4-dimensional vector. The dimension of the null space is 2. The dimension of the rank is 2. And this happens. So we've got, we've got 4 constraints, I guess, and we want to set up a linear transformation that satisfies all 4 constraints. So let's just take a look at what we're being told here. We're being told we have a vector space V, here it is. And then in this vector space, there's all 2 by 2 matrix, all 2 by 2 matrices. Draw that a little bit more neatly. All 2 by 2 matrices. Okay, so the general case one here looks like this: x1, x2, x3, x4. Okay. Then we have a transformation, L, and we end up over here in another vector space, which we've called W. And W is R4. And over here, we have vectors that look like this. They have 4 components like that. The general one looks like that. So that means if we do take L of the general matrix here, x1, x2, x3, x4, we are going to get an output, which I've now called y1, y2, y3, y4. We want to figure out what rule is, how do I figure out what is y1 from these 4 guys here, such that the criteria listed at the top are true. Okay, so what would be the most general case is I would be able to make some linear combination of these inputs. And I've got really basically effectively 4 inputs, and I'm producing y1 here. So y1, because this is a linear mapping, is going to look something like this: a1 x1 plus a2 x2 plus a3 x3 plus a4 x4. That is all the possibilities for y1. Similarly, all the possibilities for y2 is some other number, b1, b2, some other set of numbers here, b3. Okay, and then I have this is the most general possibility that I have. Okay, so I do that for all of them. This is just to sort of show you what's going on. Wouldn't necessarily have to write this whole thing out. Okay, now I know that if I take the input, as I'm told, if I take this input here, I get this output here. I mean, this is wildly suggestive of what you might want to do, but this is actually telling me that it must be the case. Now imagine here, I'm looking at this line right here. I'm like, okay, when x1 is 1, x1 is 1, so that is x1 is 1, so I'm here a1, x2 is 0, right? x2 is 0, so that guy is gone, x3 is 0, that guy is gone, and then I've got x4 is 1. So this is formed, this number right here, this guy right here, is formed by the sum of x1 plus x4. And then this next number here is formed by the sum of b1 plus b4 by exactly the same logic. And similarly, c1 plus c4 and d1 plus d4. That's the information that we're getting out of this statement right here. Well, this must be equal to 0, 1, 1, 0. That tells me that a4 is minus a1 and b4 is 1 minus b1 and c4 is 1 minus c1 and this would be d4, and that d4 is minus d1. Okay, now I have the most general thing sitting here, and I see that I have to have this constraint. Now the next thing I'm thinking about is the nullity has to be equal to 2. Nullity of L has to be equal to 2. Okay, that actually forces the rank of L to be equal to 2. Why? I have 4 degrees of freedom here. 4 degrees of freedom. So 2 plus 2 is 4. Okay, now I'm thinking about what is the nullity telling me? It's telling me L of x1, x2, x3, x4. I'm asking which one, I'm going to have some number of vectors here, that some number of inputs here that result in an output of 0. Okay, it has to be the case because this number is 2. We're told the nullity, it has to be the case that then 2 choices don't matter, right? I have to be such that there is 2 degrees of freedom. Okay, so let me then write that here like that. One option. There's lots of options here. I don't want to make out like there's. I'm just thinking through here what some possibilities are. Okay, how about this possibility right here? 0, x1, x4, and 0. Okay, that means that it doesn't matter what x2 and x3 are. That gives me a nullity of 2. And also I can satisfy this guy here if when x1 and x4 are both 1. I also satisfy these requirements here. So everything so far is being satisfied. So when I think like that, then I'm like, okay, I have found a transformation. Here it is. When the input is this, then that is the output. And you can in fact now see what the basis for the null space is. And the problem is solved. Okay, so what is the basis for the null space? We know it's of dimension 2. Looks like this. All linear combinations of these 2 linearly independent vectors. And that is of dimension 2. Because why? Because x2 doesn't matter. So in this case, x1 and x4 are both 0. No matter what number this is, you'll get the 0 vector out. And similarly here, x1 and x4 are both 0. Doesn't matter what this number is here. So all linear combinations of these 2 vectors are going to produce an output vector of 0. The null space has dimension 2, And that because we have 4 degrees of freedom, and we have the Rank-Nullity theorem, we have now forced a rank of 2, and then we have that single output that we were told right here. That thing is also satisfied. So we've constructed a linear mapping. Okay, that is a difficult question to end with. And so again, what we've done is we've done stuff in R2 and R3. We've slowly moved up to Rn, and now we've actually moved up to a little bit more of a general vector space. Thanks very much. That's the end of section 4.5.